All right, guys, today we're starting our last confidence interval section. We've done a confidence interval for population proportions, one for population mean, and now the last one, population standard deviation or variance. Just a quick review, kind of overview what's going on, what we've been doing. Let's say you have this population of certain things. I don't know what they are. Just a population of, I don't know, some sort of, just a population of items. What we do first every time we do one of these is we need a simple random sample. That's so important. If we don't have a simple random sample, no matter what we do, doesn't matter. So you can pull stuff out of here. You can pull a sample out of the population. And what you can do once you get your sample is from your sample you can find a proportion of something if you want to. That's what we call p hat. You can find the mean of your sample. And today we're going to be working on, you can find the standard deviation of your sample, which is little s. What we're going to use those for is to try to find the true p of the population, some kind of true proportion, or the true mean, which is known as mu of the population, or the true standard deviation, which is maybe sigma of the population. So basically what we're doing, taking a sample, a simple random sample. The sample must be good. Remember, no convenience sample, no voluntary response sample, a good simple random sample. That's so important. And then we use that sample to use these as estimators of something that is true about, or give an interval of what is true for the population based on what our sample was. So just a big picture there of kind of what we've been doing. All right, in this section, we're going to be doing standard deviation of variances. And think about it, when we did proportions, we did z-crit all the time. When we did sample means, most of the time we did t-crit or t-distribution, student t-distribution, unless we knew the standard deviation of the population, then we could use z-crit also. Now with this section, something brand new, we have to use what's called the chi-square probability distribution. So we can't use z-crit or t-crit, we're using chi-square crit, I guess you could say, to find our critical values, so that we can construct the confidence intervals. We're also going to look at how to find the sample size, but we're going to do that tomorrow, on tomorrow's video. Okay, chi-square distribution. First of all, in a normally distributed population, it must be with the variance that's a symbol for population variance. It's always been for standard deviation squared, which is sigma squared. Assume that we select independent samples of size n, and for each sample, compute the sample variance. Then the sample statistic chi-square has a sampling distribution that is called the chi-square distribution. I'm going to show you what that looks like. If you do all the variances from all the samples, like we did all the p hats that time when we got that normal distribution. Well, if you do all the variances, this is what it's going to look like. Well, not there yet. Here's the formula for what it's going to look like. The formula for chi-squared, that's the symbol, by the way. It looks like an X. It's like a Greek X. That's chi-square, not chi-squared, chi-square. And it equals n minus 1, remember n is sample size minus 1, times s squared, which is sample standard deviation. And then on the bottom, that's sample standard deviation squared, which is sample variance. And in my denominator, I have population standard deviation squared, which is population variance. And the n minus 1 is really degrees of freedom, which is sample size minus 1. So that's the formula for the chi-square distribution. And here's a picture of what it looks like. Notice, this is basically what it looks like right here, chi-square distribution. Notice it is not symmetric whatsoever. The bigger the degrees of freedom, the more symmetric it becomes. If you look at this picture, degrees of freedom 10, the blue one, the degrees of freedom 20 is the red one. The red one is much more symmetric than the blue one, which basically means the bigger your sample size, the more symmetric it's going to look, but it's not going to be symmetric. So some properties real quick. Number one, it's not symmetric, unlike the normal, and even the t-distribution is symmetric. As the number of, just said this, df increases, it becomes more and more symmetric. Property 2, the values can be 0 or positive. It has no negative. Now that's different also. Z-scores can be negative, t-scores can be negative, chi-square is never negative. It can be 0 and positive. Number 3, the chi-square distribution is different for each number of degrees of freedom, so you have to take that into account every time. df is n minus 1, just like we did the other day with the means. As the number of degrees of freedom increases, it gets more normal. This talks about using table A4. We're not going to use the table. We're going to try not to. We're going to use our calculators like we have been doing. So make sure you bring those with you. Quick example. All right, it says a simple random sample of 22 IQ scores is obtained. Construction of a confidence interval for the population standard deviation sigma requires the left and right critical values of chi-square correspond to a confidence level of 95% and a sample size of 22. One thing we know right away, that means our degrees of freedom is going to be 21. And when you do think about the chi-square distribution, 95%, just like it did before, is going to have a 0.025 on one side and a 0.025 on the other side. It's just not symmetric. Okay, here's the picture. There's the chi-square distribution. Notice I have the 0.025 here and a 0.025 here. Tomorrow in class, I'm going to show you how to take your calculator. And if you want to go look at it right now, if you go to your second bars like we've been doing, you will see a chi-square in there. You'll actually see the symbol. And you see a chi-square PDF and a chi-square CDF. And we're going to use those to find our values, our critical values like we've been doing. So then we can set up our confidence interval. All right, estimators of variance. Remember, this is population variance. It's not just standard deviation squared, even though that's what it is. It is called variance. The sample variance is the best point estimate of the population variance. So once we find a good estimate of our sample variance, that's a great estimator of our population variance. One thing to remember here, estimator of standard deviation. Here's the problem. The sample standard deviation is commonly used as a point estimate or an estimator, but it's not a good one. It's biased. And so what we're going to do is we're going to use the variance one, and we're going to find a confidence interval, and we're going to take the square root of those numbers to get the confidence interval for our standard deviation instead of just doing some kind of standard deviation thing. So we're working with variance today, and we're going to take the square root of it to get our standard deviation. Okay, all kinds of symbols here. Confidence interval for estimating population standard deviation or variance. And again, this is what we're going to do the most. We're going to do the variance, take the square root. So symbols real quick. Population standard deviation. If it's squared, it's population variance. Little s, sample standard deviation. S squared, sample variance. Make sure you keep them straight. Little n is the number of sample size. E is margin of error, like it always has been. Chi-squared is the left critical value with a little l subscript. Chi-squared with a little r is our critical value to the right in a chi-square. All right, confidence interval for estimating a population standard deviation or variance. Again, mainly variance. Requirements. Number one, huge. Made the big deal of this at the first slide. It must be a simple random sample. No convenience, no voluntary response. It must be a simple random sample. It's a sample. If your sample is bad, you can come up with all these numbers, but they end up being useless. You have to have a good sample. Number one, have to have a good sample. Number two, the population must have normally distributed values, even if it's large, which means our central limit theorem doesn't matter so much because we still have to have a normal distribution, which means if you look at the histogram of the sample data, it needs to look fairly normal, or don't forget the QQ plot. You can do the QQ plot and it needs to be very close to a straight line. Confidence interval for estimating population. Here's our formulas. We saw this early. This is our critical values. Degrees of freedom times sample variance over our critical value, our chi-square crit, as we would say. And then over here, that's the right side, by the way. And then over here, degrees of freedom times sample variance over chi-square left side. All right, so that's what we're that's the math. That's what we're going to do on the calc, or we can work it out. So that was for variance. So if we're going to do standard deviation, what we're going to do is we're going to do the same thing. We're going to find that variance, and then we're just going to take the square root. The only difference in this slide and the last slide is I'm taking the square root of those values, because if you take square root of variance, that gives you your standard deviation. So I hope this is making some sense, but we're doing the same process we've been doing, except we're working it out for standard deviation and variance instead of the mean, or instead of just proportions. All right. Procedure for constructing it. Here's how we're going to go. Number one, Verified assumptions are satisfied, meaning there's two assumptions. Simple random sample, number one. Number two, it has to be normally distributed even for big samples. Number two, make sure you're using n-1 degrees of freedom. It says use table A4 or technology. We're going to go with technology like we always do, and you must find these two values. Once you find those two values, you can make your upper and lower. Now, think about this. You're not really doing E. If we were doing E today, this would pretty much be it, but there's not really a margin of error. We're just finding our upper and lower levels of our confidence interval, and this is what we're going to do. We're going to plug our numbers in there because we're going to know the sample size, we're going to know the sample variance, and then we're going to calculate our chi-squared using our technology. Okay, continuing on with that, if the confidence interval of the standard deviation is desired, we're going to take the square root of those numbers, the upper and lower, like we talked about a minute ago. Number 5, we're going to round the results, confidence level units, level limits. If using original set of data can construct a confidence interval, round the confidence interval to one more decimal place. So we'll go one more decimal place than what it has. If we're going, yeah, that's good enough. We'll just go one more decimal place. Okay, one word of caution. I don't think this will affect us any, but just so you know, confidence intervals can be used informally to compare the variation in different data sets, but if you overlap confidence intervals, it should not be used for making final conclusions because you're looking at two different data sets and you can't really tell equality of variances and standard deviations when you're looking at two different data sets or three different data sets, whatever the case may be. So just be careful when you're doing that. And I don't think that'll come into play for us. All right, quick example. Same example we had a minute ago. A group of 22 subjects took an IQ test during part of a study. The subjects had a standard deviation IQ score of 14.3. Now that is the sample standard deviation. Okay, there's our n, which means our degrees of freedom is going to be 21. Directions: construct a 95% confidence estimate of standard deviation of the population from which the sample was obtained. So look at my numbers here. There's my sample standard deviation. There's my n. There's my degrees of freedom, and I want 95%. Okay. First of all, let's make sure we can treat it as a simple random sample. Number 2, I went ahead and showed a histogram, and it's pretty close to normal. I know you could do this. We're fairly close to normal there, so it's close enough to where we can say okay, but it needs to be fairly close today. The closer to normal, the better off we are. All right, so here's my numbers again. There's my degrees of freedom. There's my sample size. Instead of it says use table A4, I'm going to show you tomorrow where to find this on your calculator, the left and right side of chi-square. So there's my numbers. So there's my formulas right here. So I'm plugging them in. Degrees of freedom, 21 right here. Variance, sample variance or sample standard deviation right there. Sample variance actually because it's squared. And down here are my two chi-square numbers. And I'm just going to punch those in the calculator, work them out, and I come up here. Now, when I do that, that gives me that confidence interval here is if you look at it as sigma squared, which means it's the variance. So if I want the standard deviation, which is what the question asked me for, I take the square root here, square root in the middle, and square root here. And so my 95% confidence interval estimate tells me that the population standard deviation is somewhere between 11 and 21 and 20.4. So I could say we have 95% confidence that the limits of 11 and 20.4 contain the true value of the population standard deviation somewhere in there. All right, that's a lot of stuff today. We will work on it like we always do, but hope you got some good notes. Answer your question correctly. It should be easy for you, and I'll see you tomorrow.